clearly have kept you all waiting. Welcome. It's so nice to see you all here this evening. For those of you who don't know me, my name's Richard Florzone, and I'm Dal's 11th president. I couldn't be more pleased than to introduce to you our speaker tonight. You know, as I was walking over here, I was thinking about the words of Governor General David Johnston. He often talks about Canada as a smart and caring nation. Caring meaning that we look after those who are less privileged than ourselves, but smart also means celebrating excellence. And what a way, what an evening to celebrate excellence in the excellent scholarship of Professor Axel Becke. Let me just take a moment. I want to thank first the Killam Trust and the Killam trustees for the important work they're doing that has supported Axel's work and is celebrating him tonight. The Killam Trusts were established in 1965 by Isaac Walton Killam and his wife Dorothy J. Killam. They're one of the only private philanthropic trusts for higher ed in Canada. They fund scholarships at the graduate and postgraduate level in specific Canadian institutions. And after Mrs. Killam's passing, Dalhousie was one of only 5 Canadian universities to receive benefactions. So it's a very significant philanthropic gift that helps to advance research and support students here at Dalhousie. The prize, of which Axel has won and is the reason for his lecture tonight, is the Canada Council Killam Prizes, and they're among Canada's most prestigious awards. They recognize a lifetime contribution in the fields of health sciences and natural sciences and engineering, social sciences, and humanities. And to date, there are close to 7,000 Killam laureates now in various parts of the world. So we're just so proud, as I said, I'm so pleased to welcome tonight and introduce to you Dalhousie Professor Emeritus and the 2016 Canada Council Killam Prize winner in Natural Sciences, Dr. Axel Becke. Now, I'm really looking forward to this lecture. I haven't heard it, Axel. His lecture, Quantum Theory of Electrons in Matter, Notes, Chords, and Symphonies. I understand Axel's going to use some musical analogies to explain the fundamentals of quantum theory and also reflect on his lifelong career in science. I'm looking forward to it in this part because Dr. Becke, while I can't have come even close to his incredible scientific career, we have a common heritage in nuclear physics, in the study of nuclear physics. And so I really look forward to those stories of those analogies on quantum science and how you explain it. Dr. Becke's seminal work on density functional theory, you know, it's not an overstatement to say that it has really transformed computational chemistry. The techniques that he developed and the approximations he developed in DFT, or density functional theory, have made him one of the most accomplished scientific researchers in Canada and the world. And so some of you might know this statistic that the journal Nature did a study of the most cited papers in all of the sciences, and in the top 25, two of them were authored by Axel, single author papers. So those are in all the scientific disciplines, and citations to his work total almost 120,000 to date. So it's really an incredible scientific legacy that continues, and so we're so thrilled to hear from Axel tonight. I won't say too much more about DFT. I'll let Axel get on with that, but let me just mention a few other awards in case you're not impressed enough by the citations. In 2014, Axel was the first Canadian to receive the Premier Award in the field of theoretical chemistry from the American Chemical Society. And the following year, he won Canada's top Chemistry and Chemical Engineering Award, was inducted into the Discovery Centre, hosted the Nova Scotia Science Hall of Fame, and was the recipient of what I kind of think of as Canada's Nobel in some ways, recipient of the NSERC Gerhard Herzberg Gold Medal, a really incredible set of accomplishments. And in 2016, the Canada Council for the Arts announced Axel as the 2016 recipient of the Killam Prize in Natural Sciences. Dr. Becke held the Killam Chair in Computational Science at Dal from 2006 until his retirement from teaching in 2015, and is now engaged in full-time research. So, it is such a privilege to call you one of our own, and please join me in welcoming Dr. Axel Becke.
Thank you, Richard. I'm wired.
You're live. You're live.
I'm wired.
Thank you.
So thank you for that kind introduction, Richard. I feel a little bit underdressed, actually. Richard's wearing a tie, and Chris Moore's wearing a tie, and I'm not. But let me just show you that I can do the tie thing when protocol absolutely demands it. So this is me receiving the Killam Prize scroll from His Excellency David Johnston at Rideau Hall the evening of May 3rd. It was quite an evening. And notice the tie, and it's a black one at that. Richard was kind enough to introduce me on that evening as well. This is Richard giving his introduction speech. This is me giving my speech. In case you've never been to Rideau Hall, I just wanted to show you what the ballroom looks like in Rideau Hall. This is where the ceremonies take place. It has a beautiful golden hue. It's really a spectacular room. This is a view from the front, and this is George Cooper, who unfortunately can't be with us this evening, giving his speech. And here's a view of the room from the back. Now, this isn't actually the Killam Prize ceremony. This is the NSERC Top Researchers ceremony that took place in February 2015. But I want to show you this absolutely magnificent painting of the Queen, which really dominates this room when you're sitting there, and is right behind the Governor General's chair. All right, so let's get started with my public quantum theory crash course. I'm hoping to be able to do this in an hour, although I'm going to try to cover a lot of ground, and I do hope you enjoy it. So I'm going to start with basically high school information. So if it's been a while since you took this in high school, try to remember back about the Rutherford planetary model of the atom. 1911 is the date. And basically, it's a planetary model, quite literally, of atomic structure. We have a positively charged nucleus with a whole number of elementary charges in it, 1, 2, 3, 4, etc. And that's called the atomic number. And it is surrounded by an equal number of electrons, because each electron is negatively charged and has one elementary unit of charge on it. And this is the basic structure of an atom according to the Rutherford or planetary model. And I hope you all remember that from high school. Now, I have to tell you that the size of the nucleus here is grossly exaggerated. In actual fact, nuclei are 10 to 100,000 times smaller than the size of the atom, so it would be a bare pinpoint on this picture. But generally, people exaggerate the size of the nucleus so you get the idea of what this structure actually looks like. So that basically explains the structure of this periodic table. All right, so the number here is the number of positive charges in the nucleus and the number of the negative electrons orbiting around the nucleus. There are 92 or 94 or 91 naturally occurring nuclei, depending on who you ask and how you define naturally occurring. But that's basically what this periodic table is all about. Okay, so let's think about that planetary model for a bit. An electron orbiting around a positively charged nucleus. For the physics of the time, circa 1900, which we call classical physics today as opposed to quantum physics, there's a fundamental and deep paradox here which we have to think about. Let's consider the simplest atom, a hydrogen atom, just one electron orbiting around a nucleus of elementary charge 1. So in classical physics, that electron can have any of infinitely many different motions and infinitely many energies. I mean, it can have a variety. You think of it, any circular motion, elliptical motions. It can have any energy. And this is problematic. So in classical physics, all motions are allowed. All energies are allowed as that electron orbits around the nucleus of charge 1. That's a problem. Because we know that all hydrogen atoms in the universe are actually identical to each other. They're identical in size, identical in energy, and identical in all other properties. Similarly, all carbon atoms are identical to each other in all respects. All oxygen atoms, all iron atoms are identical to each other in all respects. So atomic motions can't be unrestricted. You can't just have any old energy as an electron orbits around a proton in the hydrogen atom. The motions have to be restricted somehow, or you wouldn't have this similarity between all atoms of a given kind. Nature would be structureless if these motions weren't restricted somehow. We wouldn't have chemistry, we'd have chaos. This periodic table would just be washed out in chaos. So how can we explain this? What kind of framework do we have in which to understand this restrictedness? And the word that we use in science is quantization. That just means restricted motions. What kind of framework do we have at our disposal in order to understand this restrictedness or quantization of the motions of electrons in atoms, which is necessary for there to be structure at all in the universe? So that brings me to the first part of the title. Notes, or in scientific parlance, standing waves or orbitals, as we more often than not call them in theoretical chemistry and physics. Louis de Broglie in 1923 proposed something quite creative, which we now know as the particle wave hypothesis. Now, I don't know if de Broglie was actually a musician, and of course I don't know what his thought processes were, but you know, musical instruments suggest something about quantization to us. And perhaps this is what stimulated de Broglie to make his bold hypothesis. This was his thesis, actually, which was published in 1924. It's got to be one of the most creative theses in the history of science. Well, let's think about musical instruments. Let's think about a piano, for example. All pianos play the same notes, right? If they're constructed according to the same specs, and if they're tuned properly, all pianos play the same notes. They don't play random notes. That doesn't even make sense, right? Well, let's think about that a little bit more. Again, I'm taking you back to high school. Maybe you've done this experiment in your high school physics course. If you take a string or a spring, we usually use slinkies in high school physics courses out in the hallway outside the lecture room, and you clamp the ends so that the ends can't move, there are only certain discrete, restricted modes of motion that are self-propagating, okay? There are no other possible motions if you clamp on the ends of a string. All other motions destroy themselves, according to something called destructive interference, which is an appropriate name. So one can have only certain allowed vibrations if you clamp a string at two ends. You can have the so-called fundamental or first harmonic vibration, second harmonic, third harmonic. The frequency increases as you go up from one harmonic to the next. And as you go up from one harmonic to the next, you increase the number of nodes. I'm going to use this word a couple of times. A node is a place where the motion is actually zero. So as you go from one harmonic to the next harmonic into higher and higher frequency, you add a node every time. So there's the fundamental, node-less, except for the endpoints. We don't call those nodes. And then 1 node, 2 nodes, 3 nodes, 4, 5, etc. Those are the only possible sustainable motions of a string that is clamped at two ends. We call these standing waves, stable waves, harmonics, whatever word you like. Now, this is a model of restricted motions, right? Only certain motions are allowed, not just any frequency, not just any motion. Now, I'm not a guitarist, but I understand guitar players know this, at least intuitively. If you pluck a string, it'll vibrate at its fundamental frequency. And I should tell you that when you see these pictures, you have to imagine these things as vibrating up and down like this, in case you hadn't figured that out on the previous slide. So it'll vibrate with its fundamental frequency, but if you touch it at one of the nodes of a higher harmonic, here or here or here, you will select that harmonic, and it will play that different frequency. So maybe motions of electrons in atoms And molecules and materials and all matter are somehow governed by standing wave principles, totally analogous to the standing waves that we see in musical instruments. All right? Only 3 years after de Broglie published his wave-particle hypothesis, Erwin Schrödinger came up with this equation, which, if you can solve it, describes the standing wave motions of electrons in matter. Electrons in atoms, or in molecules, or in materials. It's a pretty innocuous-looking equation. It's what we call a differential equation, but boy, is it hard to solve. It can only be solved with pencil and paper for a handful, quite literally, of simple model problems. But here's what it means, even though I'm not going to derive it, not going to ask you to understand it. This is the most important equation in theoretical science. This is the equation for the standing wave modes of electrons in matter. Psi I is a symbol that represents the standing wave amplitude. Epsilon I represents the energy of that standing wave motion. It's sort of like the frequency of standing wave on a string. And the effective potential here is the potential that an electron sees as it moves through matter, arising from the attraction to the nuclei and the averaged motions of the other electrons. But there's a philosophical problem here. How can something be a particle and a wave at the same time? And this, of course, as you might imagine, was hotly debated in the first few years of quantum mechanics. This is the interpretation that has withstood the test of time, the Born interpretation. We have to do a statistical kind of interpretation. There's really no way out of something being a particle and a wave at the same time. The physical interpretation of this psi I, if you can solve this equation, and we can with computers, is that the square of psi I at some point r gives the relative probability of finding the electron near that point r. So the larger is the value of the orbital squared, the higher is the probability of finding the electron near that point. So we call these orbitals. We also call them wave functions. I'm going to call them standing waves or orbitals, depending on the mood I'm in at any particular moment. So this is kind of interesting. I mean, this is a statistical or probabilistic interpretation of quantum theory. That means it's not about certainties. It's about probabilities. And that leads to all sorts of weird theorems like the Heisenberg uncertainty principle, which I'm sure you've all heard about, or most of you, even if you haven't studied science. This is not a theory. This is the only way we can interpret it, about certainties. It's about probabilities. And the probability distribution is given by the solutions to this equation for an individual electron's motion. So let's look at computer solutions of Schrödinger's equation in actual molecules. And I'm going to do a sequence of molecular shapes from the simple to the more complicated. Linear, ring, and then sphere. Let's start with a linear molecule. This is dodecahexane, 12 carbons arranged in a line. Okay, it's a zigzag line. It's not a straight line, but that doesn't really matter. It's essentially a line, partially saturated with hydrogen atoms on the outside. This molecule is actually perfectly planar. All the atoms lie in a single plane. So let's take a view of the molecule side on, and you'll see what it looks like. It's perfectly planar. Now, whenever you have a molecule that's perfectly planar, the orbitals are of two kinds. One can have sigma orbitals that lie in the plane of the molecule, and one can have pi orbitals that are perpendicular to the plane of the molecule. This is always the case when one has a planar molecule. The orbitals factor into these two classes, sigma in the plane, pi perpendicular to the plane. The pi orbitals are the most important in chemistry because they're the most reactive. So let me show you what those look like, starting with the first pi orbital. And if you can suppress the thought that this looks like a submarine sandwich, you can compare it with the sketch I gave you before of a fundamental vibrational mode for standing waves on a string. The next one nodal plane here. 2 nodal planes, 3, 4, 5. 5 nodal planes. There are actually 12 pi molecular orbitals in this molecule, but I'll stop there. I think you get the idea. And you can see the close analogy with standing waves on a string for the pi orbitals in a sort of linear string-like molecule. Let's go to a ring next. Next in order of geometric complexity. This is not my sketch. I got this from the web. It's really hard to draw standing waves on a ring. Try it sometimes. This author tried to derive standing waves on a ring by taking standing waves on a string and wrapping it around and joining the ends. That turns out not to work, because that would give you a point on the ring at which there's no motion, and that's not the way it actually goes. So let's allow ourselves to be inspired by another musical instrument. Let's have a look at standing waves on a circular drum. This is a sketch of the standing waves in energy order on the surface of a drum. Now, a ring is sort of like the outside of a drum, is it not? Or maybe just slightly inside, because of course the outside of the drum isn't actually vibrating. But you can think of a ring as being some circular slice inside this drum of infinitely small narrowness, okay? Now, because a ring has no radial structure, it's infinitely thin, what we have to do with these drum standing modes is just eliminate the ones that have radial structure, because a ring can't have radial structure. So take out that one, radial structure there, take out that one, take out that one, and what you're left with is a representation of standing waves on a ring. That actually works. So let's have a look at the chemist's favorite ring-like molecule. This is benzene. 6 carbon atoms in a ring, partially saturated by hydrogens on the outside. This molecule is also perfectly planar, so it has sigma orbitals and it has pi orbitals, and we're going to look at just the pi orbitals. First, we'll look at these straight down, okay? Top-down view of benzene as I've shown it there. And as I go through these orbitals, I'll show you the little sketch of the drum modes that I had before, which suggests standing waves on a ring. So there's the first one, nodeless. There's the next one with a vertical nodal plane here. It has a partner orbital with a nodal plane that is horizontal, and they have the same energy. They're distinctly different, but they have the same energy. We call that degeneracy. Another degenerate pair, this time 2 nodal planes, horizontal, vertical, and its degenerate partner with the nodal planes at 45 degrees. That's degenerate. And there are 6 orbitals of pi type in benzene. This one is not degenerate. It has 3 nodal planes at 60-degree angles with respect to each other. Now remember, I've just shown you the top-down view in the pictures that you've seen so far. Just for completeness, let me show you what's happening on the other side of this planar molecule. Just like you saw in dodecahexane, what's happening on the back side of the molecule is essentially the negative of what's happening on the front side. So I'll go through these rather quickly. Okay, from submarines to Kaiser sandwiches, there's that one. And then we have this degenerate pair. This is the stuff you saw before, top down. That degenerate pair. And this is the last pi orbital in benzene in its full 3-dimensional glory. Let's go to spheres, sort of. I didn't do calculations on a real sphere like C60, Buckminster-Fullerene. I wanted to keep things simple. So I'm going to look at spherical-like molecules, molecules that we call centrosymmetric. This is sulfur. You can tell it's sulfur because it's yellow. Sulfur can surround itself by as many as 6 atoms pointed towards equivalent points on a sphere. Okay? So the orbitals of centrosymmetric molecules and spherical molecules show very much the same patterns. So that's why I'm going to look at centrosymmetric molecules. I'm going to pull out some of the typical patterns one sees in spherical molecules. They're basically the same for real spherical things like C60 or for centrosymmetric molecules with stuff pointed towards equivalent points on a sphere. So first, SH6 chemists are going to say, what? This molecule doesn't exist. It's not stable, okay? But I want to surround the sulfur with hydrogens just to pull out the essential features of the, what we call spherical harmonics that characterize the orbitals of spherical and central symmetric systems. And I must say, this is one of the beautiful things about computational science. You can compute whatever you want, whether it's a real molecule or not, whether you can make it in the lab or not. We can do computations on it. Put a bunch of atoms anywhere you want in space, and we can compute the properties of that system. The charge distribution of the electrons, the energy, et cetera, et cetera. It's really beautiful. That's what I like about computational science. I can give you so many examples, but we don't have time. So you will recognize these if you're a chemist. S, we would call that. This is a molecular orbital. We call it S. And there's your px, and your py, and your pz. D, x squared minus y squared. The one we call dz squared. The dyz. You should recognize these shapes, right? They're atomic-like, but these are actually MOs in SH6. dxz, dxy. Now let's go to a real molecule, sulfur hexafluoride. This one is real, and because fluorine has a lot more internal structure than hydrogen, you're going to get a lot more interesting orbitals out of this. Let me show you just a few of the orbitals near the highest occupied, because these are really cool. This is the highest occupied, -3, -2, -1. Highest occupied. This one resides on just a 4-membered fluorine ring. So there are 3 of these that are all equivalent to each other on the 4 different 4 fluorine rings. This is the lowest unoccupied. Okay, that's a real menacing looking orbital. This is the lowest unoccupied +1, and so on and so on. I just want to impress you with how artistic and how complicated these orbitals can get in complicated molecules with lots of heavy atoms in them, like sulfurs and fluorines and whatnot. So I've shown you orbitals with characteristic shapes in some small, highly symmetric molecules just for teaching purposes. Well, we can solve Schrodinger's equation for orbitals in molecules that don't have any particular symmetry, for orbitals that are of enormous size, hundreds of atoms, and I'm not kidding. We can even solve Schrodinger's equation in materials. And the people who do this are called computational chemists, or computational physicists, or computational materials scientists, depending on their area of application. There are programs out there that do this, very complex, many millions of lines of code, but one can solve Schrodinger's equation in very large molecules without any symmetry whatsoever, using a variety of codes that are out there, dozens and dozens. Even in materials, one can do this. Next part of the talk. So, which notes do the electrons in a molecule play? I haven't really said anything about that. I've just shown you these orbitals, or what I've been calling notes or standing waves. The last molecule I showed you, sulfur hexafluoride, for example, has 70 electrons in it. Where do they go? Which notes do they play? Now, each note, or orbital, has its own energy. And the energy increases as the number of nodes increases, in other words, the complexity of the pictures. And chemists draw energy level diagrams like this to represent each orbital and its energy, from the lowest energy up. And generally, there are infinitely many orbitals in any system. They get increasingly more crowded as you go up here. Okay, but I'm just going to show you, say, the first 6 typically in these pictures. But there are infinitely many getting really crowded up here, and I'm just going to leave this arrow here to remind you there's a lot of higher energy notes. So now let's put the electrons into this picture. Let's take half a dozen electrons and put them into this picture. It would be perfectly reasonable to suggest that they should all go into the lowest energy orbital. Perfectly reasonable. You would be wrong. What actually happens is that the electrons occupy the lowest 3 orbitals in pairs. What's up with that? Well, here the planetary model gets even more literal. Just like planets orbiting the sun can rotate internally. Okay, they have a spin motion around the north-south pole. It has been known since 1922 that electrons, too, have an internal spin. And just as the motion of electrons through space has to be restricted and is restricted, it turns out that the internal spin motion of electrons is also restricted. And it turns out, in fact, it is so restricted that there are only two possible spin motions, counterclockwise and clockwise, with some predetermined value of the angular momentum, which I won't get into. But basically just clockwise and counterclockwise. That's it. No other internal spin motions are possible. We call this spin up, because that's the way the spin angular momentum vector would point, and spin down, and that's it. Spin up, spin down. No other possibilities. And if you look at it closely, the electrons go into the orbital scheme in pairs, one spin up and one spin down. You can't have two electrons of the same spin in an orbital. One has to be up, the other has to be down. This is called the Pauli exclusion principle. It's remarkable. No two electrons of the same spin can occupy the same orbital. Why? Each orbital may only be occupied by a single electron or a pair of electrons, one spin up, one spin down. There is nothing like this in classical physics, nothing at all. It's like electrons of the same spin can't be in the same region of space. They can't be in the same orbital. They sort of repel each other. And this has nothing to do with a real physical force. I mean, the electrons do repel each other, okay? They repel each other by a 1/r Coulomb potential. They have the same charge. But this effect is much, much stronger than anything that can result from Coulomb repulsion. I'll say more about that in just a moment. So this is really mysterious. It's not due to any real physical force. There's some kind of repulsion between electrons of the same spin, not electrons of opposite spin, because they can live happily in the same orbital. But there's some kind of repulsion between electrons of the same spin. We call that Powley repulsion. This can be proved, believe it or not, in a single intro quantum class at the third-year level using the mathematics of elementary linear algebra. Now, I retired from teaching last year, but this was by far my favorite class. And if you know anything about elementary linear algebra, in particular, if you know about solving linear systems and how you can do that using something called determinants, that's all you have to know to actually prove all this. It's amazing. So this is called a Slater determinant, literally. And this is what a Slater determinant looks like for the beryllium atom, which has 4 electrons in it. 1s, 2s orbitals are occupied. Alpha means up spin, beta means down spin. Don't worry about the details. This is literally a determinant. If you know anything about expanding determinants in linear algebra, you expand this by row or column, your choice, just the way you expand any determinant. This construction has built into it the Pauli exclusion principle. I can't prove it to you, but it does. You can do it in one class in about 10 minutes in an introductory third-year quantum class. This is amazing to me. This is the fundamental object, this Slater determinant, in the quantum theory of any system containing more than one electron. There's something else really cool about this. Not only does it have the Pauli exclusion principle in it, you can't construct such a determinant if any two of the electrons are in the same orbital with the same spin. It just zeroes out. But there's another neat thing about this determinant. If any two electrons have the same spin, they cannot be close to each other. The probability of two electrons of the same spin being right on top of each other is absolutely 0 in this determinant construction. That's Pauli repulsion. Very, very strong. Absolutely prevents electrons of the same spin from being near each other at all. There is no such rule for opposite spins, only parallel spins. That boggles the mind if you think about it for a few moments. This is math. Did nature take a first or second year linear algebra course? Did the people who invented linear algebra and solving linear systems with determinants, did they do it inspired by chemistry and the periodic table? Of course not. So this very, very intimate connection between nature and science is actually mind-boggling when you think about it. This Powley repulsion, that for parallel spin electrons, they can't be near each other at all, is a purely mathematical effect. And yet it's quite real. If you're a computational chemist and you try to do calculations without using these Slater determinants, you are just way out in left. You're not even in the ballpark. This is real. And yet this Pauli exclusion principle and the Powley repulsion that is so strong between parallel spin electrons but not opposite spins is math. So this really boggles the mind. If you think about it too much, your head hurts. Right? What is the connection? You know? So I'm just going to go on trusting that science is mathematics, and mathematics is science. And I will let the philosophers ponder why that should be so. I find that really amazing. That's why I love this particular class so much when I used to teach intro quantum. All right, symphonies. Scientific parlance, configuration mixing. Now things get complicated. In fact, things get so complicated, maybe cacophony is a better word than symphony. I'll let you be the judge. So in a single Slater determinant, and we also sometimes call these configurations, although there is a subtle difference in meaning. Let's assume configuration and Slater determinant mean the same thing. The electrons move independently of each other. Each electron lives happily in its own orbital without sensing the presence of the other electrons, except in an average sort of way. I mean, that picture where I put up-down pairs into the energy level scheme suggests nothing about the electrons sensing each other's motions. So it looks something like that. There's an artist's rendition of a single Slater determinant for a 3-electron system. But that's not reality. Unfortunately, electron motions are not, in fact, independent. They are to a first approximation, but they're not really independent if you think about it. Surely electrons collide with each other, right? They do repel each other by 1/r Coulomb force, so they do sense each other in an instantaneous sort of way. They don't just see each other on average. They do collide with each other occasionally, and the actual motion looks more like that. So electrons do repel each other instantaneously. Now the words here are very important. They're going to be really important in a moment. They scatter each other out of their independent orbitals. They don't live happily in their independent orbitals. They collide and they scatter each other up, out of those happy orbitals that you've seen so far when I draw the orbital picture. The difference between that picture, the correlated picture, and this picture, the single determinant picture, is called correlation energy. And as you might guess, it's really hard to compute. So here's how you have to do it. You start with the lowest energy determinant, and this is called Hartree-Fock approximation. If you just take the lowest energy determinant, and you hope this is most of the story. And more often than not, it is most of the story. It's 80 or 90 or 95 or 99% of the story, most of the time. But if you really want to compute accurate numbers as a computational chemist, you need to consider what I just said on this slide. You need to scatter the electrons out of their independent orbitals as a result of their collisions with each other. So you start there and you mix in, or linearly combine, that's what we're actually doing with the math, some of that. Hopefully a small amount, but you have to include some of that with an appropriate coefficient, which you have to compute, some of that, and not just double excitations, but anything you can imagine, single excitations, and they come in pairs. This one is partnered with that one and that one, that one and that one, and so on and so on. Wow. So the actual picture is a lot more complicated than a single Slater determinant. It's a mixture or a symphony or a cacophony of all those chords, okay, all those pictures of electrons in their energy levels. In principle, you can't do this in practice, but in principle, you need to mix all conceivable excited configurations into the lowest energy Hartree-Fock Slater determinant. Even though it's the dominant one most of the time, you have to, in principle, mix everything in. This lowers the total energy, which is kind of weird, actually. If you're really paying attention, you will notice that all those determinants we're mixing in to the Hartree-Fock have higher energy. Individually, they each have higher energy than the lowest energy Hartree-Fock determinant, but the total energy of any such linear combination is always smaller. Okay, you know what that's called? The variation theorem, for those of you who have taken quantum theory. So that's kind of interesting. In practice, of course, you can't mix everything in. There are uncountably infinite conceivable excitations of electrons out of the Hartree-Fock Slater determinant. You can't do everything. So in practice, quantum chemists have developed schemes to select only the most important. Various ways to do this. I won't go into the zoology of the many ways to do this. But basically, configuration mixing is very costly. And by that I mean it takes a lot of computer time. Depending on the size of your system, you know, look at usage of AceNet resources. These calculations can take weeks, months, if the system is large enough. It's very costly in terms of computer time. It can be done, however, for molecules, at least reasonably small ones. No way can you do this for materials. In fact, even Hartree-Fock is not routinely possible for materials. It's just too pricey. You can't even do Hartree-Fock. I mean, it can be done, but you don't do routine Hartree-Fock calculations, let alone configuration mixing in materials. So we've got a real problem here. But is it important? You can guess it is, or I wouldn't be talking about it. It sure is. Unfortunately, big yes in capital letters. If you ignore correlations and just do a Hartree-Fock calculation, you get huge errors in molecular bond energies. And what's more important in chemistry than a molecular bond? What's more important in chemistry than knowing the energy it takes to break a molecular bond, or how much energy you get back if you make a molecular? This is central to chemistry, right? A molecular bond energy. Hartree-Fock has errors of 100%. This is not like 1 or 2% error, 100% error. This is massive error. You really need correlation in molecular systems. Some molecules, like F2 and chlorine-2, aren't even stable. The energy of the F2 molecule is actually higher than the energy of the 2 free fluorine atoms. So Hartree-Fock is just not on for computational chemistry because it misses the correlation. Now, you know, you can explain why Hartree-Fock is so poor for molecular bonds rather easily. So let me give this a shot, even though it's a public lecture. I think you can sort of get this. Let's consider the simplest bond in chemistry, H2. All right, just 2 hydrogen nuclei and 1 electron of spin up and 1 electron of spin down in this molecular orbital. They have spin up, spin down. There's no Powley repulsion. In the uncorrelated picture, each electron is sort of bouncing back and forth between the two ends without noticing the motion of the other electrons. Okay? The motions are uncorrelated. They're independent. Each is bouncing back and forth independently of what the other one's doing. So it's pretty obvious, actually. 50% of the time, the electrons are going to find themselves at opposite ends of this molecule. The other 50% of the time, they're going to find themselves on the same center in this molecule if the motions are truly not correlated. This is bad, okay? Because electrons do repel each other, even if they have opposite spins. There's no Powley repulsion, but there is still Coulomb repulsion. So these situations are actually unfavorable. You might want a little bit of this to happen, but certainly not 50% of the time. So this is the problem with uncorrelated Hartree-Fock theory. You don't want these pictures where the electrons are piling up on the same center. So what you have to do is reduce the probability of this happening relative to the probability of electrons being at opposite ends of the bond, and configuration mixing accomplishes this. If you do the math, you can see that that's what happens. You basically damp this out. You don't want it to be absolutely 0, but maybe 5 or 10%. You certainly don't want it to be 50% of the story. All right. I kind of like this analogy. I haven't heard anyone else use this. So in a molecule, what the electrons are actually doing, and I think this is a pretty good imagery, They're playing a game of musical chairs, all right, in order to avoid piling up on any given nucleus at the same time. That's energetically unfavorable. The electrons have to play musical chairs and spread themselves around over the various centers and not pile up. The mathematics of musical chairs is surprisingly difficult. Configuration mixing can do this. There are other methods out there. Physicists love this game. There are a variety of methods to handle this game of musical chairs. They are all difficult. And in fact, this kind of correlation is so prevalent in molecular systems and also in solids and materials, we give it a special name. This is called strong correlation, as opposed to other kinds of correlation one can have inside an atom in a molecule. That's called strong correlation. And it's really important. Let's look at some numbers. I'm going to show you some numbers from a benchmark set of accurate experimental atomization energies. Atomization energy means the energy it takes to burst a molecule into free atoms entirely. In other words, it's the sum total of all the bond energies in a molecule. So this is a measure of your ability to compute bond energies, because this is a data set of the sum total of all the bond energies in 148 of your favorite molecules. You know, water, ammonia, methane. They go about as heavy as benzene and substituted benzenes. And this is accurate experimental data, not theoretical data. So this is good stuff. There's the reference. Numbers. Hartree-Fock, one configuration only. This is the best you can do. These are average errors I'm showing you. Okay? Mean absolute errors, average errors. The best available number crunching, correlation, you know, configuration mixing, blah, blah, can get you an error bar of 1 or 2 kcals per mole. That is really good for a practicing experimental chemist. This is more or less, so keep this in mind. Don't worry what a kcal per mole actually is. Just remember that our target accuracy in computations is 1 or 2 kcals per mole. We would really like to get that, because experimentalists would really like to have that kind of accuracy. Hartree-Fock, 160. No way. But the best available methods can do it. They are very costly. They can take days, weeks, months of computer time. Small molecules only, as I mentioned before, impossible for materials. So are we stuck, or is there something else we can do? I would like to introduce now an astounding theorem that was presented by Walter Kohn and his collaborators Hohenberg in 1964 and Sham in 1965, called density functional theory. Now, if you will allow me to be technical for a slide or two, because this is really important stuff. This is what I've been doing for 35 years. In their 64-65 paper, Hohenberg, Kohn, and Sham rigorously proved that you can define an independent particle reference state for a correlated system in which the total energy can be written like this, and these 3 terms are essentially classical physics terms, so those are really easy. And all the dirty stuff, the Powley repulsion, the correlation, is swept under the rug into a relatively small term called the exchange correlation energy. Now, at this point, I'm going to switch from Powley repulsion to exchange, because that's what we call it in density functional theory. Powley repulsion and exchange are essentially synonyms for each other, because the Powley repulsion effect in the Slater determinant comes, believe it or not, by exchanging orbital electron labels inside that Slater determinant. So exchanging labels has everything to do with Powley repulsion. It's very subtle. So when I say exchange from here on in, I'm talking about Powley repulsion effects. So this is called the exchange correlation energy. It's got all the dirt in it. It's got all the dirt in it, all the tough stuff. Now, this formula is not remarkable as it stands. It's just a definition of the exchange correlation energy. This is the astounding part. They proved that this energy, which has all of the exchange and correlation effects in it, depends only on the total electron density, where that is a sum over all the orbitals of the orbital densities. In other words, you don't have to know what the individual electrons are doing. This is astounding. You certainly have to know all that when you do configuration mixing, because you are literally mixing all these different configurations with the electrons in different orbitals. And wow. In fact, in principle, all of that information is contained in just the total electronic density. Even in a material where you have an infinite number of electrons, in principle, all of the information is contained in the exchange correlation energy, and that is derived just from the total density in principle. You don't have to know about the individual electronic orbitals. You just have to be able to sum them up and get their total density. So, appropriately, this is called density functional theory. Astounding. For which Walter Kohn was awarded the 1998 Nobel Prize for Chemistry, even though he was a physicist. I think it surprised him as much as everybody else, with John Popel, a name that will come up again. In other words, in DFT, there's just one Slater determinant. There's no configuration mixing. Whew. But you have to dress this Slater determinant with additional information in the exchange correlation term. Here are the classic references, which I have to give you for completeness. And notice that the theory is just a little over 50 years old now. And this is why I really love DFT. There's more. Hohenberg, Kohn, and Sham did not know this in the mid-1960s, but at least half a dozen authors derived this result in the mid-1970s, about 10 years later. There's a beautiful intuitive content in density functional theory that is not in configuration mixing. One can show that the exchange correlation energy is related to this is really the last technical slide, the really technical one. It's related to a two-electron function in real space called the exchange correlation hole, and this is how they are related to each other. This is beautifully intuitive. Let me try to describe to you physically what the exchange correlation hole is. It is a function that measures the extent to which you repel other electrons from your vicinity as a consequence of Powley repulsion and correlation effects. So I can imagine myself as an electron moving through this auditorium, and as I move through this auditorium, there is an exchange correlation hole surrounding me that tells me how I am pushing other electrons away from my vicinity. It is a measure, and this is absolutely rigorous. As I plow through the system, this exchange correlation hole is a measure of how I repel other electrons away from my vicinity. This is absolutely rigorous. Now, this is something you can intuit. I can imagine plowing through a material and pushing the other electrons away as I move through that material. But that's very intuitive. But of course, configuration mixing is not intuitive at all. Some people have an intuition for that, not me. We call that configuration space. This is a beautifully intuitive, real space interpretation of exchange correlation effects. So one of the games you can play is to try to model this thing, and I've been doing it for 35 years, and then putting it into this expression and getting exchange correlation approximations. Very, very powerful. So, you can draw pictures of it. In a uniform density electron gas, which is a model system we can imagine, if you're an electron here, there's the exchange correlation hole. It looks something like that. And this is how you repel other electrons away from you. You deplete the probability of finding other electrons near you. That's why it's called a hole, because you are depleting the probability with respect to the uncorrelated probability of finding other electrons near you. Pauli repulsion, Coulomb repulsion, you deplete the probability. That's why it's called a hole. It can get very complicated, even in H2. Here is the hole for the electron just inside the right-hand nucleus at 3 different distances between the nuclei. And you can see how the hole changes shape. It also changes shape, I should say, I forgot to mention this, as you move through the system. So this hole depends very much on where you are in the system. Its shape is constantly changing as you're moving through the system. So this is a beautiful intuitive tool, and I love it. What's the catch? This is almost too good to be true. In the early days of DFT, I used to say there is a free lunch, but there isn't. Here's the problem. The Hohenberg-Kohn-Sham proof is essentially an existence proof. There is no simple formula for this thing, or a complicated one. There is no formula for the exchange correlation energy. It's an existence proof, let alone a simple one, and there never will be. This is the nature of existence proofs, isn't it? Okay? Quite often, you do an existence proof, out comes an incredibly profound result. but you rarely get explicit formulas for the thing that you proved exists. And this is the nature of the Hohenberg-Kohn-Sham existence proof, that the exchange correlation energy is in principle a functional of just the total electron density. Okay, so what do you do? The best we can do is find approximations by various means, and there's many means, I won't go through them, and hope that we get better and better approximations with higher and higher accuracy. That's all we can do. There's no exact formula, let alone a simple one, never will be. Now that's important though. You have to have an existence proof. You don't want to waste 35 years of your life, like I have, looking for better and better approximations to something you don't know exists. So this is really, really important, even though we don't get an exact formula for this thing. Kohn and Sham themselves proposed in their 65 paper the local density approximation, the simplest possibility. More about that in a minute. Oh, now a little historical perspective. HKS were physicists. They didn't actually care about atoms or molecules. You know, Walter likes to tell the story. He was interested in metals and alloys at the time. That's why they invented this astounding theorem. So basically, Kohn-Sham DFT was ignored by chemists. I mean, they didn't even know it, let alone ignore it. It wasn't even on their radar for more than about 20 years. But I was interested in it for reasons I don't have time to tell you. And I started testing Kohn-Sham DFT on molecules and atoms in the mid-1980s. And it was an interesting exercise. And I've been studying exchange correlation energy and holes ever since. So let's have a look at this journey. And I'll try to do this fairly quickly. I'm sort of getting towards the end, don't worry. All right, let's look at this G297 atomization energy test set again, the sum total of the bond energies in 148 different molecules. There's Hartree-Fock, 160. Local density approximation, 1965, Kohn and Sham. That's about twice as good. But it's still way, way off the mark. Remember, our target accuracy is 1 or 2 kcals per mole, so that's not going to cut it. Now, this is a bit of an oversimplification, but let's put the local density approximation into perspective. Basically, it's an integral. You integrate over every point in your atom or molecule or material, and the integrand depends only on the value of, these are spin densities, spin up electrons and spin down electrons. At each point in your integration, the integrand only depends on the value of the spin densities at that point. That's called the local density approximation. And it really doesn't work very well. Now, the next logical thing to do, if you have a mathematical frame of mind, is, say, a Taylor expansion. Let's think about integrands that include not just the density, the spin densities at each point, but also, say, the gradients of the density. It's like a Taylor expansion. Now, we can actually do the Taylor expansion, but it doesn't work very well, so you have to be a little more clever. So we have designed a variety of approximations of this form that are not literally Taylor expansions, but they involve the local density and local density gradient. And so because they're not Taylor expansions, we call them generalized gradient approximations, or GGAs. I published 3 papers on GGAs in the mid-1980s. This was the last one, 1988, and in my opinion, this was the last word in exchange GGAs or Powley Repulsion GGAs. I really love this functional. It fits atomic data better than any other functional in the universe ever since or before that time. So that is known as the infamous B88 exchange GGA. Now, exchange dash correlation means that, you know, the Powley repulsion and the correlation effects are different. One involves parallel spin electrons. The other involves opposite spin electrons. They are physically different effects. So we can have GGAs for correlation as well. And I'm not going to say anything about those because actually their effect on molecular properties is absolutely insignificant. It's the GGA for exchange that makes all the difference. You can pick any correlation GGA you like, and the numbers hardly change at all. So it's the exchange GGA that really matters. So hereafter, when I say GGA, I mean that B88 exchange GGA plus PBE correlation. That's not me. This is Perdue, Burke, and Ernzerhoff. Just for completeness, that's what I mean by GGA. But it's this thing that makes all the difference. All right, let's look at these numbers again. Wow. Hartree-Fock 160, LDA about DFT, GGA, 10 times better than the local density approximation. And did you see what that functional looked like? It's incredibly simple. Even the Hartree-Fock energy formula is a lot more complicated than that. So that is really compelling. An order of magnitude improvement over the LDA. But the chemists still weren't interested. I'm sorry, I might go 10 minutes over. I hope you're enjoying this. So, you know, science is a human activity, as are all things. And sometimes it's about being in the right place, at the right time, with the right person. I want to take you back to 1991, to the International Congress on Quantum Chemistry in an absolutely beautiful town on the French Riviera called Menton. Menton is right at the border with Italy, and it has the French Alps right behind it. And I'm going to show you a few pictures of this town, and the reason is the following. There is increasing pressure on me, and I'm sure all of you, to confer with your colleagues by Skype, net meeting, you know, virtual conference software of various kinds. I'm old school, and I want you to resist, because I'm resisting as best as I can. Confer the good old-fashioned way. Real face-to-face meetings in inspiring places like this. I mean, if places like this don't inspire your science, I mean, I don't know what to say. It's a beautiful town, numerous beaches and marinas. The conference center is quite close to the old town, so if you take a walk in between sessions, this is what it's like. It's beautiful. You also have to be very fit. This is a very hilly town. And like that, beautiful place to visit. And I just love French flans. And this is actually an appropriate segue to what I'm about to say next. At this meeting, I had a 3-hour, I'm not kidding, 5-course lunch conversation. 5 courses, only the French can do it this way, with a certain individual. 1 or 2 days before this conversation, I can't remember exactly how many days it was, I had presented at this conference GGA test results for the first time on this individual's G1 thermochemical benchmark set. This was the predecessor set to the G297. This has 148 molecules. This one had 55. The person I had this conversation was, and this was pure coincidence. It wasn't planned. I walked into our hotel dining room at lunch one day, and he was seated by himself. And I screwed up the courage to ask if I could join him. I was just a neophyte at the time. This guy was enormous. And he said, please do. And we chatted for 3 hours. We talked about a lot of things. The person I had this conversation with was this man. And if you're a chemist, you know who this is. This is John Popel. No doubt the grandfather of computational chemistry. He shared the Nobel Prize in 1998 with Walter Kohn. We talked about a lot of things. I won't give you the details. We came from different communities, so we aired a lot of dirty laundries. But, you know, he must have taken home a few messages from our conversation, because within a year of that conversation, he and his coworkers published a paper in Chemical Physics Letters in which they implemented B88 plus another correlation, GGA, Li-Yang par, but remember that part doesn't really matter. And they released this functional in a computer code known as Gaussian. And they came out with a special release. Gaussian came out with a release the year before, and they usually come out with releases every 6 or 7 years. After Gaussian 92, they came out with a special release. This is unprecedented. Gaussian 92/DFT. They've never done anything like that since. Now, you have to understand how important this is. The Gaussian program, which is John Popel's baby, okay, that's why he's the grandfather of computational chemistry. This program is ubiquitous in chemistry. I mean it. It's like the Microsoft of computational chemistry. Love it or hate it. You cannot avoid it. It's everywhere. And so now, starting 92, not just mainstream quantum chemists, But every chemist virtually in the world could do DFT calculations. What a scary thought that was for me. Because the Gaussian program is used not just by theoreticians, but also by experimentalists. I think it's fair to say that in every chemistry lab in the world, there is probably a copy of Gaussian running on a PC somewhere in the corner of the lab. And so everyone could now do these DFT calculations. This was the breakthrough moment for DFT. I don't know what would have happened if we had not had that conversation. I really don't know. This was the breakthrough moment in chemistry, but also in physics and material science. Strange though it may seem, even though cone-sham DFT was invented by physicists, they didn't embrace it themselves. They embraced something called Slater's X-alpha, which I won't get into. It's not cone-sham DFT. So the physicists themselves did not embrace cone-sham DFT for at least 20 years until after the chemists had embraced it. And boy, did the chemists ever embrace it. So this is one of the papers that Richard was talking about in his introduction. I've shown this to you before. It's just a reprint of that B88 GGA I showed you before. The last time I looked, 10 days ago, it had accumulated about 32,000 citations. And in October 2014, Nature commissioned a study honoring the 50th anniversary of science citation indices. They commissioned Web of Science to identify the top 100 cited papers of all time in all the sciences. And this one came out at number 25. If you don't believe me, there's a link with the entire paper there and an interactive list of all of the top 100 papers. So the chemists really did embrace this. How many papers is that? All of science, all 58 million papers. That was in October of 2014 when Nature commissioned this survey. Then in 1993, another minor breakthrough. Now, I can't go into the details of this. Hartree-Fock exchange and cone-sham DFT exchange are not quite the same thing. There are differences. And I was able to provide arguments in this 1993 paper that we should mix in a little bit of the Hartree-Fock exchange and swap out a little bit of the DFT exchange. There are really good theoretical reasons to do that. This is an even bigger hit than the B88 paper. So in that October 2014 Nature ranking, this came out as the 8th most cited paper of all time. And 10 days ago, it had been cited about 60,000 times, and it gets cited 8,000 new times every year, at least at present. Why is this such a hit? Well, now we're doing even better than the GGA, like 2 or 3 times better. And now we're starting to approach that desired chemical accuracy of 1 or 2 kcals per mole. We're not there yet, but this is extremely useful, nevertheless. And consider that before density functional theory, Hartree-Fock was the standard starting point in computational chemistry. These hybrid functionals have error bars 50 times smaller, and the cost is about the same as a Hartree-Fock calculation. So that's why this paper has been such a hit. Only 7 years after it was published, people were writing things like this. My friend Krishnan Raghavachari, one of the co-authors of the G297 set, along with John Popel, that this paper has had an astonishing impact on the entire field of quantum chemistry. This is 7 years after it was published. All right, I'm almost done now. So what have I been working on lately? A lot of my friends say, why do you keep on working? I mean, just take up golf and go to the beach. But there's still a lot to do, an awful lot to do, and it's compelling work that needs to be done yet. I haven't said much about radicals. I've told you the electrons can pair off, 1 spin up, 1 spin down, in molecules that have an even number of electrons, but there are molecules that have an odd number of electrons. These are called radicals. I'm oversimplifying a little bit, but essentially, let's say that a radical is a system that has an odd number of electrons. These are highly reactive and highly transitory because electrons really do like to pair off up and down spins. But these are important in reaction mechanism chemistry. So these are something we need to consider. Every time I show this slide, I'm afraid people will flee from the room and stop using DFT forever, because this is really embarrassing. Things are not bad near the equilibrium separation, okay? But this is the simplest radical in chemistry. It's a hydrogen molecule. Just pluck off one of the electrons. It doesn't get any simpler than that. It's H2+. One electron in the field of two nuclei. That's it. It doesn't get any simpler. And look at how DFT screws up as you pull this thing apart. Truly embarrassing. But again, in defense of DFT, it's okay around here. And, well, H2+ is the worst conceivable case for what we call delocalization error, which is the problem here. So I was thinking about delocalization error for a long, long time. This problem really has to be fixed because I'm sick and tired of showing this embarrassing slide. BO5, I don't have the reference there, doesn't matter, is a sort of superhybrid that performs just as well as hybrids, maybe even a little better, and it is much better for radicals. That's the whole point of BO5. For example, BO5 gets it bang on. I mean, it does the exact dissociation curve. It is much more reliable for radical systems, and that was the point of BO5. So BO5 is not terribly popular, may never be, because it's extremely complicated. It's much more complicated than hybrid functionals. So I don't know if it will ever be a hit like hybrid functionals, but boy, it does the right thing as far as radicals are concerned. But there are immense technical challenges with implementing these things. But I'm a theoretician. I'm worried more about getting the theory right than whether or not it's easy to code up. So there's BO5. It's good for radicals. Then, at around the same time, we were working on dispersion interactions. I did this with one of the best graduate students in the history of graduate students, Aaron Johnson. Believe it or not, around the year 2000, there was no density functional theory of dispersion interactions. Now, what are dispersion interactions? These are very weak intermolecular interactions, often called van der Waals interactions. These are the interactions that attract molecules to each other. So they're much weaker than the forces that bind the molecules together themselves, but there are very weak attractions between molecules, dispersion or van der Waals interactions. Aaron and I came up with the first density functional theory of van der Waals interactions, including dispersion effects, in a record 3 years, from 2004 to 2007. And that was an accomplishment of which I am very proud, and so is Aaron. Now, these are weak interactions, so are they important? You bet. Even though these are the weakest interactions in chemistry, they are of paramount importance whenever molecules get together to form complex aggregates. And chemistry in this century is all about complex aggregates, if you look at the applications of what chemists are doing in labs these days. Biology is all about molecules forming aggregates as a result of dispersion and van der Waals interactions. In fact, if you turn off the dispersion interaction in the double DNA helix, it unwinds and becomes a ladder. That's how important it is, the weakest interaction in chemistry. That's another beautiful example of computer experiments that you cannot do in nature or in the lab. You can actually selectively switch off certain interactions in a computational experiment, and there's no double helix in DNA if you turn off dispersion. It's just a ladder. That's how important dispersion effects are in aggregates, as you find in biology. Also, nanoscience, surface chemistry, it's all about aggregates, dispersion interactions. A lot of complex functional materials these days are structured according to dispersion interactions. Incredibly important stuff. So Erin is now working on wonderful applications in all of these areas of our dispersion theory, and she's now a professor here at Dalhousie. She's been here since last July, and I'm really proud that she's here carrying on this great work with some really good applications on the go. B13. This is an extension of BO5 to handle, I'm almost done really, to handle multi-reference states. What does that mean? There are some states in chemistry, few, and these really happen during the course of chemical reactions, not equilibrium structures, but during the course of a chemical reaction, it is often the case, in fact, it's almost always the case, that a single Hartree-Fock reference determinant does not suffice, even as a first approximation. It's not 80 or 90% of the story. It might be less than 50% of the story. This is called multi-reference, and I really do think this is the last frontier in DFT. I've been experimenting since 2013 with this functional that I think can handle multi-reference, but I'm not sure. I'm still working it out. This is ongoing research. And this is what I'm working on like right now, most currently. In fact, I got the publication notice of this paper just yesterday. So this is really new work. I've been looking at a novel approach to the computation of excitation energies in density functional theory. What that means is how molecules interact with light. So an interaction means something like this. Start off with a molecule in its lowest energy reference determinant and input some energy, light energy, thermal energy, whatever, and kick this one up, say, 2 energy levels to that one. That's called an excitation, a single particle vertical excitation. This has obvious applications whenever molecules interact with light. So photochemistry, light-emitting devices, solar energy, lots of applications of this theory. All right, photosynthesis, all that kind of cool stuff. But you know, maybe you've got the sense from this talk that I'm not so much interested in applications as I am in fundamentals. And the reason I really like this problem of computing excitation energies is because it is, in fact, the simplest conceivable multi-reference problem. So let me show you how that works, and this really is my last science slide. If I kick an electron up from this level 2 levels up to that one, there are actually 4 Slater determinants I can imagine that have almost the same energy. Depends on how you orient the spins. So I can have up, down, up, up, or down, down. That doesn't violate Pauli, right, because these are in different orbitals. Each one of these, as I said, has almost the same energy, and not even as a first approximation should you think of taking just one of those or any one of those and think of it as a good first approximation. You have to mix them together. So this is actually the simplest multi-reference problem in computational chemistry, and that, in fact, is why I'm so interested in it. It sort of fits in with the work I'm doing with B13, multi-reference chemistry. And that's it, okay? So let me just conclude with a couple of acknowledgments to people and organizations who have been helpful throughout my career. Russ Boyd has been my Dalhousie mentor ever since I first came here in 1981 as a postdoctoral fellow. I was postdoc here from 1981 to 1984. This is where I actually began my work on cone sham DFT. This is when I started publishing my first exchange GGAs. By the time I published B88, I was at Queen's, but this is the place where it all started. And I have been using those ideas that I generated here for 35 years of my career. They just get more and more complex as time goes on. But this is where it all started. And Russ Boyd was my mentor since 1981, since forever. More recently, Marianne White has been very helpful to me, and I acknowledge her assistance as well. At Queen's, where I was from 84 to 2006, Vidine Smith Jr. was my mentor there. And I have to mention my good friend and colleague, Dennis Salahub, at the University of Calgary, who actually put together my Killam Prize nomination package. I have a very short list of students and postdocs. Half of my papers, maybe more than half of them now, are single authored. So this is the sum total of all the students and postdocs I've had. I have highlighted the ones that are here. Ross Dixon was, you're out there somewhere. I think I saw you before. My very first graduate, hi Ross. My very first graduate student at Queen's was Ross Dixon. He's now here at Dalhousie. He's with AceNet. I'll mention them again in just a moment. And Aaron Johnson, I have already mentioned, is a professor here in chemistry and physics. I would like to acknowledge the funding agencies that have been research partners for my entire career. NSERC, you all know about NSERC, but equally much. And I've done sort of back-of-the-envelope calculations, and I think that monetarily, I have received as much support from the Killam Trusts of the Canada Council and Dalhousie University as I have from NSERC. Both of these are major funding partners throughout my entire career. And I want to thank AceNet, for which Ross works, the Atlantic Computational Excellence Network for truly outstanding computing and software support. Now, I want to say more about the Killam Trusts because, as I've just told you, they have been immensely beneficial throughout my entire career. It was a Killam postdoctoral fellowship that brought me to Dalhousie in the first place as a postdoc from 1981 to 1984. Then I went to Queen's for 22 years. It was a Killam chair in computational science that brought me back to Dalhousie in 2006 until last year when I retired from teaching. Killam chair in computation, 9 years. That is an immensely valuable award. It paid my salary for 9 years, and I am immensely thankful for that. In 2005, 2007, during my transition years from Queen's to here, I had a Canada Council Killam Research Fellowship. This is one of the most coveted Killam awards that any senior academic in this country wants. This buys you 2 years of unfettered research time. So I am truly grateful to the Canada Council for that 2-year Killam Research Fellowship, and earlier this year, of course, the greatest honor that can be bestowed by the Canada Council and the Killam Trust, the Killam Prize in Natural Sciences. And that takes me to the end of my talk. So, in case you're wondering, this is a photograph of all 5 Killam Prize winners at the very end of the ceremony in Rideau Hall, when we were in a good mood and we were looking forward to the reception. That's me, Isabelle Donat, Humanities, Elizabeth Edwards, Engineering, Stephen Nayrod, Health Sciences, Daniel Treffler, Social Sciences, and with that, I thank you for your attention.
So I'm Chris Moore, I'm the Dean of Science, and I have to say I'm so immensely proud to lead the faculty that Axel is a member of. He has just been a superstar in our faculty for so many years. You know, listening to the talk, I'm a psychologist, so you know, a lot of it went over my head, but listening to the talk, you can't help but be impressed by the passion for his science that this man still has after so many years. I mean, I was really excited listening to it. So Axel, congratulations again.
Thank you, Chris.
Thank you so much for this talk, and it's our pleasure to have you still at Dalhousie.
Thank you.
A little gift from us.
Okay.
We will not have Q&A right now because of the time, but there is a reception just out to the doors and up to your right. And I'm sure Axel will be there, and you know, you may have a chance to chat with him there. Okay, thanks so much.
If you like, I'll stick around down here for a bit if you want to come down here and ask questions. Thanks, Chris.